Thank you so much, everybody, for joining us for today's Protocol Labs Research Seminar. Today, we are joined by Katharina Kohls, an assistant professor in the digital security group of the Radboud University. Before Kohls as a professor, she worked as a postdoc researcher at the System Security Chair for the Ruhr University Bochum. Kohls' research focuses on information leaks in networks. One example of this is specifically Tor, where the persisting threat of traffic analysis attacks remains an open issue and motivates research on new offensive and defensive techniques. Besides dedicated anonymity systems, Kohls is also interested in the consequences of transferring well-known attacks to new contexts like LTE. So thank you so much for joining us today, Katharina, and I'm going to let you take the presentation over from here.
Yeah, thanks a lot for the introduction. Thanks a lot for having me. I'm happy to give this talk for the very first time. So this is a project I worked on with Claudia Diaz from the KU Leuven in Belgium, who's also with NIM Technologies. And this is actually a project that we worked on the last 2 years, and it's going to be published and presented at Usenix, but that's like in the summer, in August or so. So this is the very first time giving this presentation, talking about this project. So let's see what happens. So it's about a system called VerLoc, Verifiable, Localization, and Decentralized Systems, and that's one of these standard, boring, cryptic research paper titles. But all of these components actually make sense, and we'll get to this in the next minutes. But to get warmed up, I'll begin with a bit of a story time. And in our story, we have Alice over here, and then we have Eve over there, and they are good friends, and they live in different parts of the world, but they stay connected, and they exchange information, and they talk, and all that good stuff. And now Alice wants to send a book to Eve. She wants to send a very special edition of 1984, her favorite book, and it's a very, very special edition. So she wants to send that book via mail to Eve so that she can read it and get to see all the nice images, whatever that is in that special edition. And Eve says, okay, don't send it directly to me, send it to my good friend Socks Guy, and he'll send it over to me. Because, I mean, they live in different parts of the world, and in between there is Evil Town, and Evil Town doesn't like this book. Evil Town doesn't like books and stories like this in particular, and if they would just send it straight away, it will go through Evil Town, and they will probably just take the book. So Socks Guy say, okay, they need me because the book might get lost on the way, and Evil Town doesn't like it. I will take care of this. I'm close to the border, I'm outside, I'm safe here, I can pick up the book and I will send it to Eve. So that's good, that's a nice plan, so the book can be sent and it's safe. But in the meantime, we find out, okay, Socks Guy isn't Socks Guy, it was Monster Guy all along, and he's sent from Evil Town. He'll grab the special edition and just keep it. So what happened here? We have our good friend Socks Guy, but there is someone impersonating him, actually from Evil Town, and just grabbing the book and keeping it. Which means we don't have a happy ending. The bad guy wins. So Monster Guy is the winner in our story. And this is the problem statement. This is what the talk is going to be about. But no worries, I'll get a bit more technical in the next minute. So this is our warm-up story, and we can transfer that to context that you might know. So what you see here in the picture, that is a nice graphic of the Tor infrastructure. So if you go to that website, I'm not sure if you see my mouse pointer, but if you go to that website, you'll see this nice animated Tor flow thingy with all the different relays, and then with the traffic going back and forth. And this is just standard Tor settings. So if we now take our story and throw it on Tor as a use case, what we have is we'll just build a standard connection in the Tor network, and we can put in our characters again. So we have Alice over here, and she wants to send traffic, in our example, the book, to Eve over here. And then in our story, we had Socks Guy as a relay, And it's the same for the Tor use case. Again, so socks guy is one of the relays, just responsible of forwarding our traffic. And then if everything is fine, we can just send our traffic and it goes through the Tor relays. Everything is nice and fine and it arrives at the destination. But if something goes wrong, just like in our story, it might happen that socks guy is not who he claims to be, but a relay is not where it claims to be, but it might be in a different location. So it might be in a location like Evil Town, where we wouldn't trust our Tor traffic with because they don't like Tor and they would block it, filter it, censor it, try to do something with it. And that's a problem. So we just want to send our traffic, want to send it on its way. We have Tor, we kind of trust the infrastructure. We trust it with some sensitive information, but then on the transmission path, there's one node pretending to be in a different location. And we say, okay, that location is fine, we trust it, but it's actually not there, but it's in Evil Town. We would have never trusted Evil Town with transmitting our sensitive information. And because Tor is such a big distributed infrastructure, it's kind of difficult to just know for every single relay how much we can trust them. That's actually also in other use cases a big problem. So again, we have our bad guy here pretending to be someone else, pretending to be in a different location, and this leads to a security issue for just using Tor. And now as the final part of the story, we'll come to put the same story, the same use case to a very abstract setting now. We are not in the Tor context anymore. Let's just assume one very generic network. So we have a couple of nodes and they are somehow connected to each other. So we don't have 100% connectivity, but we have a pretty good setting here with different connections between the nodes. And because all of this is about locations, we can just say, okay, 3 of the nodes are in one nice area of the world, and then 3 other nodes are in a different nice area of the world, and we totally trust them. We say, okay, they can transport our traffic. And 2 of the nodes are in something like Evil Town. So they still have nodes, they still contribute to the infrastructure, which is nice, but we wouldn't trust them with our most sensitive or other information. So we wouldn't want to transmit traffic through their nodes. So if we want to reach a node and we can't make a direct connection, then there are different options. And in the setting, we would just say, okay, there's one relay in Evil Town. Let's not use it. Let's take an alternative connection. That's fine. We don't pass through that untrusted area and everything is fine. Now we come back to our initial problem. What if a node claims to be in a nice place, but actually is in Evil Town? We can't check that. We don't know that. We just know that the node claims to be in a nice place. And we don't know for sure if it's actually there or not. So problem is, again, server lied about location, and we have no way of verifying this or actually knowing that this is happening. And then Tor and other networks have a large worldwide infrastructure with a lot of different nodes in many different locations, and it's not all bad. We can trust the majority of nodes, but we know there are some nodes that we cannot trust, some nodes from malicious operators, and these nodes might lie about their location and they might do something that we don't want to let happen to our traffic. So what are examples of this? So far, we only talked about a made-up story and some abstract network thing, but this is something that is actually relevant for real-world systems. I just have 3 examples here, but you can transfer this to many other networks as well. So Tor, we already talked about this. NIM is a network that is comparable to Tor, so it's also an anonymity system with a distributed infrastructure, and other systems like Bitcoin, because they have a worldwide peer-to-peer infrastructure, and they have a blockchain. And it's, again, important where the nodes are located. So we have these networks in other systems as well. So, for example, these two categories, anonymous communication networks or peer-to-peer networks with a blockchain, where you would say it's actually quite nice to know where the nodes are located and to have some amount of trust in this information. And in the best case, not just some trust that you get from looking at some information and saying, okay, I trust this node, but something that you can actually verify. And this brings me back to my cryptic, boring research paper title, and now it probably makes a bit more sense. So we have in the title localization. This is about localizing nodes, really geographical locations of nodes. We have verifiable because we want to verify their locations. We don't just want to trust them with self-reported data or geo-IP. We want to verify this. And we have decentralized systems because doing this in a decentralized system is A, it's actually more fun, because B, it's more challenging, and C, then you don't need something like a trusted third party that just goes around and checks everything for you. And that's what we want to achieve. That's what we did with our system. So what are our goals from this, like these three buzzwords? First, we heard it's a decentralized network. So we have a couple of nodes. They connect to each other, and there's no such thing as a centralized authority. There's not one point where you can just go and ask, but every node is kind of responsible for their own decisions. Then we have a system where every node has a location, and as a starting point, they self-report their locations. Could also use geo-IP from the IP addresses. In the end, you have something like ground truth information where you cannot be sure that it's correct. And the goal is that we want to verify these locations. So we have self-reported data, and then in the end, we want to know, okay, can we trust this, or is there something that smells fishy here? So these are our goals for the system. And the problem is, or the challenge is, we assume that not all nodes in our system are benign. So we assume some malicious nodes that claim false locations because that might be beneficial for them, and that manipulate the system, so that try to interact with whatever we do to verify node locations. And this brings me to my to-do list. So how can we achieve this? Step one, we want to localize nodes. How can we do this? How can we do this with as little overhead as possible? Step two, we want to verify the results because we want to get some trust, like self-computed trust into node locations. And we have to prepare for trouble because we assume attackers. And three, we want to decentralize the process. So we want to be able to throw this on a system that doesn't have one single trusted authority. And we'll go through this to-do list step by step, and we'll begin with how the hell do we localize nodes on a network? And that's actually quite simple, and we use a very cheap approach here. We use round-trip time measurements. So when we have two nodes, A and B, then we send a round-trip time measurement from A to B, and then wait for the packet to come back and just measure the time. And we do it from B to A at the same time. So we always do pairwise measurements, which is nice because if something goes wrong in the measurements from A, we still have the data from B. If there is a lot of noise in the measurements from A, we still have the measurements from B. If there is different route for both measurements, we can still compare. So we have these round-trip time measurements done from both nodes at the same time. And as I said, it's quite cheap because you can just use ICMP. It's a protocol that already exists. The packets are very small, and it's an easy way to get the round-trip time to any destination on the internet. And these timings are something that we can use to translate it into distance. And distance is good because we want to localize. So what you can do is take the time that you measured times a certain speed that you assume, and then you get the distance as a result. So if A and B measure the round trip time, let's say it's 10 milliseconds, and then we assume a certain speed, like the speed of light, because nothing travels faster than the speed of light on the internet, then we can put everything in our equation, and then we have speed of light times 10 milliseconds, which results in around 3,000 kilometers. And that means within 10 milliseconds, we can reach everything within a circle of 3,000 kilometers. And now you probably say, okay, nothing travels with the speed of light on the internet, and that is correct. We are much slower, but that's okay because overestimating for our cause is nice. We are super safe when we overestimate because we can't go further than 3,000 kilometers in 10 milliseconds, and that's our upper bound. So how can we localize with this? We measure the round trip time, and then we have this ginormous circle. And then we measure the round trip time again from a different node. We get another circle. And then we do it again, we get another circle. And now you already see where I'm going with this. We get this intersecting area. And this area is where all the nodes agree with their timings. So this is an area that you can reach for all the timing measurements of all the nodes. And this is the area where the target node must be located. So B is the one that we want to measure. It must be inside this area. Looks okay, but it's not perfect. It's a quite large area, and E is also in this area. But that's not a problem. We can just add more. We have more intersections, and then the area gets smaller. And then we have this target area, and we know this area B must be located. And that's already enough for our system because we are mainly interested in countries. So if we have a country A that we don't trust because their law says, I want to observe anything that is from Tor, I want to block anything that's from Tor, then we just have to check, is this in the bad country or not? So localization, check. That's easy. We use round trip time measurements, which are quite cheap because we just use ICMP. From the time we can derive a distance. We overestimate like hell because we use speed of light, but that's okay because that makes our estimation safe. We find this intersection, and then the more nodes we add, the better the target area because we just have better data. So localization, check. And little to no overhead because ICMP, and that's an okay solution. Second step, how to verify. So we have all these timing information. How can we now verify a node's location? How can we do so if there is an attacker? So we are back in our example, same nodes. We want to localize B, but now B is an attacker. And we have the physical location, which is on the left, and we have the claimed location, which is on the right. So B claims to be where the red dot is, but it's actually in a different physical location. And now we do our measurements again, and we measure some round trip times from the 4 reference nodes. And we get this intersecting target area, and we say, okay, B needs to be in this area. The problem is B claims to be somewhere else. This kind of contradicts our measurements because if B is on the right, then the distance between A and B is longer, and it should take more time to reach the point, which means for A and B and all the other nodes, this contradicts the measurements. So what we expect is not what we get from our measurements. And that's good. We can use this to say, okay, we have estimated the location of B, and it's not at all where it claims to be. That's a problem. But our attacker is smart. It just doesn't only claim false location, it can also manipulate measurements, and that can be done in two directions. So if we look at the example of A, then we see the measured time is 15 milliseconds, but expected would be 20. And the attacker knows that as well. So what we can do, we just hold back the ICMP echo request and wait for some time and send it back and make it longer. And then it looks like 20 milliseconds, and it looks like the claimed location instead of the real one. That's easy. The other way around is difficult. We cannot speed up measurements. We can't just make the ICMP echo request go faster. That's not possible. And that's a problem for the adversary. So you can delay messages and you can delay the round trip time, but you cannot speed it up. And this still leads to results that where the expected and the measured differs. And this is a characteristic that we can use to identify false claimed locations and manipulations. So verification, we have to assume that some nodes claim false locations. Okay, we have to assume manipulations, and slowing down is easy, but speeding up is not. So that's still a problem. That's something that we can use. And to verify something, we actually compare the claimed and the estimated location. We compare the measurements, and then we see, okay, there's so much strange stuff going on with the timings. Something must be wrong. And this says that our second item on the to-do list is also checked. We can verify node locations. The final to-do is bring this all into a decentralized setup. And that's pretty much straightforward. We just need something like a broadcast channel. That can be a blockchain. I know that's a bad word. Can be a blockchain, but it can also be something else. We just need a channel that can be accessed by everyone and that is 100% transparent. So what happens? We have our network, nodes do measurements, upload their results, do measurements, upload results, do measurements, upload measurements, upload. And all the measurement results are in the broadcast channel. They are publicly available to everyone in the network, which means every node can just fetch the measurement results and do the verification that we also just looked at. And this means every node can do its own computations and then say, okay, this looks fishy. I don't trust node B anymore. And this decentralizes the entire setup because we can share the results and then we can do our own computations and then we're done. We don't have to trust anyone doing this for us. So decentralization is also checked. And now the big question is, or the assumption is, this is never going to work. You just simulated this. Yes, we simulated this and simulation worked well. But real networks are too noisy. So you have a lot of delays and stuff going on that makes your timings bad, and then estimation doesn't work anymore, and you can't localize and all that stuff. So we built a prototype in a real network to show that it actually works in practice, and that you could just use this concept for any decentralized system where you need verified locations. And for this, we used the NIM network, which is, again, you have an infrastructure of a lot of nodes worldwide, and they connect to each other. And we just implemented our prototype in these nodes and then did measurements in the real network with it. So our prototype uses a special version of NIM that adds these measurements. And the special version just says, okay, you do periodic round-trip time measurements, you send ICMP echo requests, and you get a random list of targets that you should measure. So you get your homework to do, you just do measurements, and then you upload your results. And then each node just published their results and hosted the results actually at their own address at a certain port. So you could just fetch the results. You can still do this. And we use self-reported locations as the claimed locations. You could as well use geo-IP, so that's just the claimed. And then we compare these claims with the estimates that we did. And we use in our setup 200 echo requests, which means we have a couple of measurements, and then we use the minimum because the minimum is the most optimal one, the least noisy measurement. And then what we saw in our results is that we achieve a median localization error of 60 kilometers, which is quite nice because we have noisy data. We have a lot of routing going on. I mean, we don't have these direct connections as in the picture. And 60 kilometers is okay because we did our measurements in Europe because you have a lot of small countries. And 60 kilometers is something that you can actually use, which doesn't kick you in the next country just by accident. So 60 kilometers is still fine, even in the Netherlands. So prototype worked quite well and demonstrates also that this uses can work with actual round-trip time measurements in a noisy network. And this brings me to the lessons learned, like the take-home messages of my talk. So our problem statement was we have an arbitrary decentralized network, or at least distributed network, with nodes. All of them have locations, and some of them can claim a false location for different reasons. And simply trusting this information is not an option because they transport sensitive data. So our goal was to verify these claims. And then the steps that we need to accomplish for this is we need to localize nodes with as little overhead as possible. And for this, we used round-trip time measurements. We wanted to verify what they claimed as their locations. And we want to have a very robust estimation to be sure about our decision. And we want to decentralize it. So we want to make sure that we don't depend on one node, one authority doing this, but give every node the responsibility to do it themselves. And we use a broadcast channel for that. And then we build a prototype to demonstrate that this is not just a simulation, but it could actually work. And we saw that with around 60 kilometers of location error, this is something that would even work in Europe, where you have a lot of tiny countries close to each other. And if you want to look at the paper, I'm not sure if it's officially published yet, but on my website you can get the paper. And that concludes my talk, and I'm happy to answer questions.
Wonderful. Thank you so much. That was great. I know
you.
you said this was the first time you've given this presentation, and I got to say, from someone who's not a super technical background person, you did a great job, and I know exactly like what you were doing, and I know why it's important, and that was wonderful. So thank you.
Okay, thank you.
Yeah. So now we're going to take questions. If anyone has some questions and they don't want to be on the recording, feel free to put them in the chat, and I will read them out for you. Or if you want to be in the recording, just unmute yourself and feel free to ask.
What's the structure of the ICMP pings? Is there a way that you prevent someone from being like Cloudflare edge worker, where they're actually in multiple locations, and being able to use that to pretend it?
That's something we didn't consider. So what we considered is adding a nonce to the pings, because otherwise, if you would send the ping and the target node knows that there will be a ping incoming because you know the schedules, you could just send your response in advance to speed up transmissions, and that's why we add a nonce. But we didn't think about hardcore internet infrastructure challenges.
Makes sense. That definitely makes it harder once the adversary's actually got multiple places that they potentially can be. Are there ways, if your measurement is only on like 1/2 of the RTT as opposed to the overall RTT, are there ways to make this scheme work there? And just like in terms of thinking about some of the problems we've been staring at, if you've got nodes that have large amounts of data, it's very expensive and slow for them to move that data. So they can compute sort of a proof of location of like they've got some data at some place. And if you can somehow interleave that with ping-like latency measurements, you can maybe start to get closer to proving that the data is at the place.
Yeah.
But if you've got an unknown latency in the middle there, suddenly you need to be looking at one direction pings rather than the full RTT.
By one directional ping, you mean not the round trip, but like the one trip, one trip time?
Or just because if you've got any variability, suddenly your imprecision really will magnify that,
Yep.
you know, because of that hard drive latency, suddenly you're not 60 kilometers mislocated, you're potentially way too far.
It also, I mentioned that we, like in my example, I used the speed of light, but in the system, we don't use the speed of light. We use actually a empirical propagation model where we sample how speed and distance are related to each other, because it turns out longer distances are faster, because transatlantic, they don't have a lot of routing going on. And for something like this, you would also adjust this propagation model. And one trip timing is not a problem by definition, because in the end, it's just time and distance. And for round trip time, you just divide by 2, and for one trip, you don't. So by adjusting the propagation model, you could also get a better estimate there. So in the end, it all depends on the propagation model that you assume, and the assumption you can make on transmission speed.
The other trick that, or the other hard part we ran into with one direction is now you have to have synchronized clocks, because it's not a single node's measurement on one clock. It's 2 different nodes that have to understand what their relative offsets are.
I mean, in our system, we just assume that there is an epoch like thingy that synchronizes the nodes, or that it at least says, okay, this is a new epoch, and then everyone should start measuring now. Which is, well, you can go without that, because it's a very tricky assumption to make that every node in the network is synchronized, but it's something that actually really helps with verifying stuff.
All right, thank you so much for joining us today, Katharina. We had a great time having you for the Protocol Labs Research Seminar. I know, like I said in the beginning of the questions, but as a non-technical person, I really enjoyed the conversation because I was definitely able to follow along and understand what you were exactly doing and understand the actual real-world implications of the work you were doing. So that was great. For anybody else who's watching on YouTube, feel free to go to our GitHub website. That'll be down in the summary, and you'll be able to find out all the upcoming talks we have. And also feel free to give us a follow on Twitter @Proto Research to be able to get any and all new updates that we have for our research that we're conducting here at Protocol Labs. So thank you again, Katharina, for joining us today. We really appreciate it, and we hope to hear from you again soon.
Thanks for having me.